Hello and welcome everyone to Ironville, a show where we look inside Tragibidal, an interesting new database which does quite a few unusual technical decisions, like for example implementing the whole thing in Zeek, avoiding any kind of dynamic memory allocation, or assuming that the storage has a storage fault model that the hard drive used in your database might actually at some point, return you garbage data and not actually return you the data you have written to it before. So today is the third consecutive episode where we talk about compaction, and as usual, it's going to be very in the trenches, very code-filled episode because compaction is just a lot of logic which you need to get compacted into your head. So okay, let's briefly recap where we are at. The overall structure of compaction is that it is, for Tragibidal, is that it is not, as usual, a background process like some kind of like a thread which just runs once in a while, but rather compaction runs as a part of a normal commit process. So when you accepted a prepare which contains 8,000 transfers, and after you have processed 8,000 transfers, you are going to run a little bit of compaction. And which fraction of compaction to run exactly is determined by the so-called compaction interval, compaction ops. So basically, every 32 prepares, a single round of compaction should get completed. So what we kind of like colloquially call in Tragibidal by the name compaction is like the process of compaction between two compaction ops, those 32 bits. And what is this round of compaction? Well, it is pretty simple. We have LSM tree with one in-memory layer and 7 on-disk layers. And our task when we do compaction is to do the minimum amount of compaction required to proceed to the next compaction round. Specifically, while we are running compaction for 32 bits, the new prepares which arrive at meantime are accumulating in the in-memory table. And by the time this compaction interval 32 finishes, we need to have a free space in our 0th layer on disk to accommodate the freshly built in-memory table. So the idea is like, and now let's think backwards. The idea is that by the time we finish the compaction, we have one free slot in our 0th layer. If that means that if our 0th layer is full at the start of compaction, then we need to move one table from 0th layer to the 1st layer. But the problem here is that our 1st layer also may be full. So actually, like, if we start moving from the 0th layer to the 1st layer at the start of our compaction, then we might realize that actually there is no space in the 1st layer. So what we actually need to do is to start moving from the 1st layer to the 2nd layer. And that kind of like, creates the second problem, like what if the 2nd layer is full? So what we are actually going to do is that we are going to split our compaction interval into two halves. The first half, first 16 bits, and the latter half, the other 16 bits. Then, in the first half, what we are going to do is that we are going to compact one table from level 0 to level 1, then one table from level 2 to level 3, one table from level 4 to level 5. And in the second half, we are going to compact one table from memory level to level 0, then one table from level 1 to level 2, etc., etc. So basically, the invariant is that by the end of compaction, we have at least one free table in every even layer, which allows us to append the in-memory table to the 0 layer, and also to start running the first half of the second compaction, which would compact all the odd levels into even levels. Okay, so let's get started again. The entry point is a compact function in the forest, and this compact function runs a single bit of compaction. So it's not like the single invocation of compact completes the whole 32 bits. No, like it is called, like, during a single compaction, this function is called 32 times. And within this function, actually most of the work is delegated to the so-called compaction pipeline. And this is what we were looking at last time. And here, kind of like before we, like, do any kind of compaction work, we need to, like, well, actually, I must be sharing my screen by this time. Yeah, sorry. But actually, like, we haven't missed anything important yet. Yeah. So the important part of, like, compaction work is that we need to start compacting. Like, for example, when you decide that you want to move one table from level 0 to level 1, well, you need to figure out which tables on the first level this candidate table intersects. And this is, like, one-time setup work at the start of that part of the compaction which needs to move the table. So this is what we do at the beginning of this bit function. If we are at a boundary where we need to start new work, so we are at the first bit or at the middle of the compaction, then we do this bar setup. And there we kind of, like, started looking at this, like, second half. So when we are compacting into level 0, that means that we are compacting from level -1, that is in-memory table. And this happens at the second half of a bar, but kind of, like, logically, you would love to think about this as actually, like, the start of compaction. And here, first of all, we find the range of tables which intersect our in-memory table using mutable table compaction range. Oh, actually, okay. I probably, yeah, using key min and key max from our mutable table. And well, and yeah, kind of like, well, it's slightly more complicated. Well, we want to move tables from in-memory table to the first on-disk table. Obviously, because we have an invariant that in the zeroth layer all the tables are disjoint, we cannot just, like, push our table because, well, it might intersect some table of level 0. So what we actually need to do is that we need to figure out all the tables which are intersected, and then we need to read them from disk and merge them with our in-memory table and write a new set of tables which are going to be disjoint. And that is where we stopped last week. So we kind of like found tables which are overlapping with a given key range. But then we have this extra bit of logic which is table coalescing. So basically the idea is this. Let's say that like you have like your in-memory table, and let's say it intersects a couple of tables on disk. But it so happens that tables are actually almost empty. Like, normally you would have 8,000 times 32 transfers in a single table. But if for these 32 prepares, all the prepares actually contained much less than a full batch of 8,000 transfers, your table might contain as few as just 32 transfers. So it might be the case that, yeah, kind of like you want to compact a bunch of tables, but actually, like, they are very, very empty, and the resulting table is also going to be empty. So in this case, we are going to do the so-called table coalescing. I'm not sure how exactly this logic works. We're going to find out. But the idea is that we kind of like artificially extend our ranged tables which do not actually intersect our in-memory table, but still which make sure that the resultant table is a bit more full. Okay, let's figure out how this works. Okay, what is a value count here? Okay, yeah. So a value count is the number of items in the in-memory level. Okay, so here I think we are going to estimate the total number of entries in the resultant tables. So kind of like, naively, you just sum all the tables which are inputs, which are a bunch of tables from level B and one table from level A. But it kind of like, it is important to realize that what? It is important to realize that this is an upper bound. So all these values, so kind of like, so if we do like this would be like a lower bound, because all these values are distinct, they are disjoint, so there is no way we be able to compact them. All those values are going to end up in the resultant tables. But the values from level A might actually shadow some of the values from level B. So like in the worst case, yes, we add all these values, but in the best case, actually, they all annihilate with some value from the next level, so we actually end up adding 0 values. Okay. And okay, so we kind of like what is our percent? Okay, 50. So okay, so we kind of like computed like the upper bound on the number of values which could be the result. And if this number is less than half of a full table, then we are trying to run some coalescing. Okay. And I guess we are trying to extend our range to the left and to the right. Okay, so we are finding the next table. We look at the count of values in the next table. If we could add this table to our count without overflowing the result, then okay, we edit. Not sure. Not sure what this boolean is doing here, but okay, let's take a look here. Okay, and then we like basically iterate. Okay, yeah. And if kind of like we reach the table which like overflows thing, then we stop trying to coalesce in this direction. Okay, now okay. Okay, yeah, then basically this is just like some login. So we kind of like figure out how we can extend our tables, unlock this, and then actually finish our setup. So this is, well, this is compaction range. Okay, I'm lost. I'm lost where we are. So this was table mutable compaction range. We are calling this from. Okay, yeah. So yeah, now we can continue our bar setup. So we figured out which tables we should merge our input table with in the zeroth layer, which is all the intersection tables, plus potentially some like a bunch of small tables for coalescing. Okay. We actually let's take a step back. I don't see where do we like we here like we assert that we are not trying to merge too many tables. I'm wondering where are we counting the tables here basically. So why these range tables assume append assume capacity would not actually fire. Oh, right, yeah, because here at the start, if we figure out that hey, we actually already picked up maximum amount of table which we could coalesce, then yeah, just don't try to coalesce more. Okay, and kind of like as usual, it is helpful to think about where the upper bound comes from here. So you see these tables in the compaction range, they are bounded by the LSM growth factor. This is because, so like what is the LSM growth factor? If level A has X tables, then level B has at most X times LSM growth factor tables. And in this situation, because in the both levels tables are disjoint, you are actually guaranteed to find a table which you can sync in the level down, which intersects with at most the same growth factor tables. So we kind of like have, like if we pick the table which intersects the smallest number of tables, then the worst case number of tables we could get is this LSM growth factor. And kind of like for coalescent, we just like try to like optimistically extend it. Okay. So we figured out range. Then we compute again the estimate of like the maximum number of values which we might have to compact. What else do we have here? So table info A is like which table we are going to merge from, and this is either a table on disk or in memory table. So in this case, this is in memory table. Range B is what we are going to merge into. This is always table on disk. Drop tombstones. What is drop tombstones? Action must drop tombstones. No, I don't need this. Action must drop tombstones. Okay, yeah. So, kind of like, as a reminder, what are tombstones? In LSM tree, you could only append new data. So when you want to remove something from an LSM tree, what you do is that you actually insert a tombstone. Like if you want to drop key equals 5, value equals full, you insert key equals 5, value equals tombstone into LSM tree. And those tombstones are, during compaction, they propagate to the levels below, annihilating everything that's below them until they reach, like, you know, the bottommost level. But there is optimization, like, you know, if you know that no tables below current level are going to intersect with what you currently have, you actually, like, you know, you could drop the tombstone immediately because you know there is no any value which could be shadowed by the tombstone. So this is what we do here. So okay, we're going to compact these tables from this level. We go for all the other levels, which actually could be written something like this in modern Zeek. So we start with level B plus 1 and go up to constant LSM levels. Okay. And we try to find a table which intersects with our entire range of tables. And if there is no, so if there is such table, then wow, our tombstones might shadow something. So it would not be safe to drop them, and we say, hey, don't drop tombstones. But if for all the levels below us, there aren't actually any tables there, well, we could say, hey, go and feel free to drop the tombstones. Okay, perfect. And that kind of like completes our bar setup for level 0. Setup for other levels should be similar, except that our level A is not in an in-memory table, which is table immutable, but rather an on-disk table. So what do we do here? Okay, I guess we determine, which tables should we compact. Compaction table. Let's see. compaction table range. So again, I haven't seen the definition of the struct, but I think this will contain a table reference for a table in level A, and at most LSM growth factor references to the tables in level B. And yes, this is exactly it. We have a reference for table A and reference from table B. So what does this function do? We have two levels, level A and level B. We want to sync one table from level A down to level B. We need to figure out which table from level A we are syncing. We could sync any one of them. And once we figured out the table, we need to select all the tables in level B which intersect our table. So let's see how we do this. So table count max for level, I think it's just the power. Yeah, it is just the power of LSM growth factor. Then we look at the levels from level A and level B. Okay. So we does it have -1? No, it doesn't have -1. Okay, so if the number of tables in our level is less than the number of tables this level can accommodate, then okay, then we actually don't have to compact anything and we just return null. Otherwise, okay, yeah, we find the table with least overlap. That is what I was telling you, like in general. Like, you know, it's kind of like, it should be like some kind of like gearhead principle. Like, so if we have like tables like this, and then table like this. Okay, let's do something like this. Okay, let's say our growth factor is 3. So the worst case we could do is that we have like 2 tables on the first level and with growth factor 3, 6 tables on the second level. And it could be the case that, like, you know, some table from the first level overlaps a whole bunch of tables from the next level. So, like, you know, this table overlaps 1, 2, 3, 4, 5 tables. Well, 5 tables, should be 6. Okay, let's make 6. But if this table overlaps 6 tables, then this one naturally, like, you know, can overlap only 1 table. I don't fully understand why this works. I guess, okay, so what is the worst case? I guess the worst case is that like some tables like overlap like 2 tables from a previous level. So the worst case is going to look like something like this. Kind of like, you know, for like whenever, like, you know, there's like 2 neighboring tables in the level A, in the level B, we have a table which overlaps both of them. But okay, so, and like, you know, and so like, you know, and like here, like in this interval, we actually have, like, you know, LSM growth factor multiple of tables. But yeah, kind of, you know, however, you may try to shuffle, like to pigeonhole the tables, like the pigeons, across these holes. The least overlap table will contain at most LSM growth factor overlaps. Okay, there's probably, like, you know, some kind of like more formal proof is required here to like like, you know, formally say that, hey, kind of like a table can intersect at most two tables, but, well, whatever. Feels intuitive enough. Okay, anyway. Table with the least overlap. How are we going to do this? So we have level A, level B, and we need to find the table which overlaps the least number of tables from level B. Okay, so yeah, apparently we're going to do just like, you know, stupid loop. Let's loop over all tables from level A, and for each table, let's figure out what is the tables from level B which intersected, and whether it is less than max overlap tables. So remember, our tables overlapping with key range takes an upper bound of like how many tables you might return, and if we exceed this upper bound, we just return null. So okay, so if the range contains more than max overlapping tables, we return null. Otherwise, we continue. And so if we don't continue, we find this optimal. And if the new range count is less than optimal count, then we update the optimal. So that's basically, you know, a find a minimum by the key. Finally, yeah, that's interesting. If we found a table which doesn't overlap anything in level B, so which could just be like, you know, moved, then we like finished. Okay, and this is like the key. We like return optimal table as usual. Dot question mark is Zeek's operator for checked null dereference, and this is like, you know, pigeonhole principle. Pigeonhole principle, or Dirichlet principle, that, like, you know, there's, well, it's embarrassing. I think Dirichlet principle is, like, you know, one of the first like non-trivial mathematical facts which I've learned many years ago, and I kind of like don't remember like the nice formulation. Well, I guess. Well, never mind. Basically, you could ask Google what is pigeonhole principle. Okay. Anyway, let's get back to our pigeons tables. Okay, we found. No. Where we were? Okay, we are. Okay, I'm lost. So let's go back to bar setup. So we were here. Okay, compaction table. Okay, we found our least overlap table. And actually this table with least overlap, like already, yes, it already returns the range which this table overlaps in level B. So yeah, we say that, hey, we're going to compact this table from level A with these tables from level B. So it's interesting that, like, you know, this seems like, you know, the type here and the type here are actually isomorphic, and probably we could have used a single one. Okay, so we got our we figured out what we want to compact, and then we say, okay, we are going to compact from this table A on disk to this range of tables which are always on disk, as usual, like drop tombstones if there aren't tables further down which could intersect with our tables. And this is the maximum number of values which we could produce. We might produce less, but we are never ever going to produce more. And that's basically it. Okay, move table. What is move table? Do we have move table here? Okay, so move table. Move table is optimization, which says that, okay, if your table A doesn't intersect with anything with a table on level B, you could actually, like, just move this table. You don't need to compact anything. And in the case where level A is also level on disk, like move table is pretty easy. We just say that, hey, the range is empty on level B. And if you're compacting from in memory, then move table is necessarily false, because, like, what does move table physically means? Move table means that, hey, the table is remaining on disk as is, and we just adjust the record in the manifest. We say, hey, manifest used to say that this table belongs to level 3, now it will say that it belongs to level 4. But that means that, like, the table already needs to exist on disk. And if we are compacting table immutable, which is an in-memory table, it doesn't exist on disk. So we actually, like, have to go and write it to disk first. Okay. And what do we do here? Okay, and yeah, basically, like, if we want to move table, then actually we just, like, go and do this right away, because we don't do any I/O. So we oh yeah, right. So we like go and so I was expecting to see, like, a pair of operations, like we remove from one level and add to another level, but actually it seems like we just say explicitly that, hey, this is a move table operation. And what is the type of this thing? Table info. Does table info record a level? Okay, this is oh, okay, yeah. Okay, yeah, I get it. So I'm surprised here, because we actually like, don't record a level here. And, like, obviously, if we are operating with manifest, we need to tell our manifest, like, what level we're going to do here. But actually, I lied to you, because this is not the update of the manifest. So this manifest entries is a field in our compaction bar. So this is like a state which compaction maintains in memory during a single bar, and it is the set of entries which we are going to append to the manifest when the compaction ends. So kind of like we just record that, hey, we need to apply this to the manifest. We don't actually go and apply the operation to the manifest immediately. And as usual, like, what is the maximum number of entries which could be applied to the manifest during a single compaction? Well, let's see. So I'm actually not curious. I'm curious, like, this is round for the entire bar. So each compaction can append LSM growth factor plus 1 entries. And there are levels compactions. So I would expect this to be equal to LSM growth factor times LSM levels, plus or minus 1 here and there. And let's see how wrong I am. Okay, it is just LSM growth factor, because this tracks only a single compaction, not, like, the entire batch of compactions. Well, okay, I'm wrong just by a factor of 7. That's not a big deal. Okay. And here, like, one of the invariants of a compaction is that, it's kind of like bathtub equation, that all the values you have read are the values you have written. So we track those invariants in this source values read, source value merged, source value target values merged, and targets values write counts. And if we move table, then we apply these operations logically. So we just say them. Okay. So actually this would have been clearer if written like this. So if we are dropping, if we are compacting the last table, then yeah, we must drop tombstones. And this completes our setup. So what are we actually setting up? Okay, compaction, yeah. Compaction is a compaction from one level to another level. Let's get back to the call side here. Okay, so we invoke this bar setup for every compaction. And compaction are iterated by trees and by levels. So we decided that, hey, we want to run a particular compaction, and it is a compaction for this level, and it compacts from this table or in-memory table to this range of tables. And that sort of completes the bar setup. And we store the result in our compactions array. So compaction, tree compactions are just memory allocated from compactions. In fact, we always have the same constant number of compactions, but they are not always running. Compactions in the forest, compactions in the compaction pipeline, on the other hand, are the compactions which are running. And this is actually this is curious. This is another case where we play this game of dynamic versus static type, because if you see here, we are using an inline for to iterate over all the trees, because trees have different types. Trees store different objects in their tables. And I believe that the compaction for every tree, let's actually go and see this. Yeah, so compaction is a tree-specific type. Compaction is parameterized by a particular tree. So this type of compaction is different for every iteration of this outer loop. But on the other hand, compactions here have the same type, compaction info. And compaction info is exactly the thing that type erases this information. And the key thing is this tree ID. So I think here tree ID is comp time, and here tree ID is runtime. Let's see how tree ID is set up. Well, it's just tree ID. But important thing here is here we are type specific, we are tree specific, we are compaction, but the result compaction info doesn't actually depend on the tree, which is good. Okay, so we've done setup. That is great. Now we need to go and actually start running compactions. And now and And now we come to, actually complicated stuff. Okay, what are we going to do here? Okay, I'm at loss here. Well, okay, it seems like we have some more setup to do here, because again, this is something we do on the first beat or the half beat. What do we do? Oh, yeah. Actually, this is cool. We are going to set up bar setup budget here. So okay, let us orient in space and time. So we have done setup for each compaction. So if we are, say, half bar, then we compact into even layers, and for each even layer, we figured out which is the table from the old layer we need to compact into it, and which are the tables from the even layer it intersects with. So we kind of, we need to, say, merge one table from level 3 with like 6 tables from level 4. And we have the estimate on the total number of values we might produce. Because, well, we just, we looked at the sizes of input table, the sizes of output table, and we know that the result is between the sum of the output tables and the sum of the output tables plus the size of input table. And as a reminder, this setup happens like at the beginning of a half bar. And we need to run the actual compaction work for the remainder of this half bar, where the compaction work is basically we need to read data blocks, various blocks from the input table, and we need to read various blocks from the output table, and we need to merge them together and write the results to disk. So that's like basically a whole lot of input to output. And we need to somehow spread this input output across the entire bar. Because, we would have let's remind that our bar is 32, our half bar is 16, so we have 16 ticks to do this work, and we should try to evenly spread it out. And this is what bar setup budget is doing. Okay, let's see what is happening here. So apparently we have something called block pool, which I am not sure what it is. What is FIFO compaction block? So block pool is a linked list of blocks of some kind, which I don't know what it means. Yes, okay, so let's kind of gloss over this. Then apparently, yeah, we have a set of compactions which are active in this bar. What is compaction bit set? So it is the sort of total compactions, and compactions are like the number of trees times the number of levels. Okay, which compactions are active? Okay, so we go through all of our compactions. Okay, so this is on the first beat and the half beat, and kind of well, we basically check that here is kind of first beat and odd levels, and half beat and even levels. Okay. If we want to move table, then we no need to do our budget in setup because, well, we know that we actually don't going to do any kind of I/O. Block count, block pool. Okay, I kind of like still don't understand what it is doing. Okay, well, now it kind of like makes clear. So apparently we would like, you know, oh, well, actually, what is this thing? What is block pool? Okay, block pool is a FIFO compaction helper. FIFO of compaction block, and compaction block is, well, block, read, and write. Okay, yeah. So apparently this is okay. Yeah, okay. Now I think it's kind of like becoming more clearer to me. Okay, so compaction needs to read blocks and write blocks, and that means that it needs to transfer data from disk to memory, and this block FIFO is a pool of blocks for input output. So okay, let's see what's happening here. What is this 2? It's kind of, what? So okay, so we have like block FIFO. We okay, so you are seeing how my brains are boiling live because I'm sort of still very confused by this code. Okay, well, we picked a block for immutable table A, whatever that means. And we did somehow like 2 more blocks, target index blocks. Like what? Okay, so that's kind of like, let's pretend this didn't happen because I don't understand what's happening here. Then we send this compaction is active, and probably this bar setup budget will make us slightly will shed some light here. Okay, so what is happening here? Like, we basically want to invoke bar setup function on a compaction type. Again, the problem here is compaction is parameterized by tree. So for every tree, we have a separate compaction type. And this kind of loop, like, you know, it just loops it loops over like runtime number of compactions. So we need to jump from like runtime loop to a comp time loop. And this is what we do here. So we take our tree ID, which is a runtime number, and we write an inline switch over this tree ID, which is essentially like, if tree ID equals 1, then do something. If tree ID equals 2, do something else. If tree ID equals 3, do something else even more. And the core thing here is like, you know, each do something else might use different types internally, because like in the machine code, it's just like, you know, copy pasted blocks of if. So, okay. And we do this tree compaction function. which takes, like, this comp time to ID and returns the compaction corresponding to this tree. So tree compaction takes the tree ID and the level, and together tree ID and the level identify compaction, and then it goes into that tree and fetches compaction from that level. And the only complicated thing about this thing is that depending on this tree ID, the return type might be different. Which is like, okay, exactly what is happening here. And then we do this bar setup. Bar setup budget. What happens here? Okay, we have our compaction. We have maximum bits which must complete the compaction, which is compaction interval divided by 2. Do we have like this FIFO which we pass by values and this compaction block? Oh, wait, what? So block pool, what does block pool contain? Block pool is compaction block FIFO. And this is a FIFO which contains compaction blocks and compaction. Where? Okay, I'm lost here. So, target index block. It says here that this is block FIFO. How can it be a block FIFO? Okay. How could it be a block FIFO? Well, okay, yeah, because it's... Okay, yeah. Why are this in the opposite order? Okay, so this thing is this thing, which is indeed block FIFO, and this thing is that thing which was actually first, which is actually the compaction block. Okay, kind of like makes sense, but not really. Okay, so what do we do in this bar setup? It seems like we don't actually do all that much here, so we just basically assign fields that aren't actually setting up any kind of budget. Okay, this is... Okay, this is confusing, and this is mysterious. Okay, so let's just just be honest and say we don't understand a thing in this entire block of code, and that we will revisit it later once it becomes clearer what we are actually doing. And again, we are at an hour, so probably makes sense to finish it here. Okay, so let's recap what we did today. And again, like, this is compaction, so this is going to continue for several more episodes where we just try to dig through this thick layer of code which forms the core of TigerBeetle. Okay, so we figured out how we set up budget. So before we compact anything, we need to figure out what are we even compacting. And that means figuring out which table we are compacting from level A and which table or level B are intersecting our table. And the algorithm here is pretty simple. We go through all the tables on level A and we find all the tables on level B which intersect this table from level A, and then we pick the table A which intersects the smallest number of tables from level B. And by the pigeonhole principle, given that the level B is at most LSM growth factor times larger than level A, we have a table in level A which overlaps less than LSM growth factor tables in level B. Additionally, when we compact, and only when we compact in-memory level into level 0, we try to extend our range in level B to make sure that the resulting output table isn't mostly empty. So kind of like, if we figure out that the total size of our tables is actually adds to less than a table, then we try to coalesce this a bit. And that is basically it. So this is where we stop. We figure out, like, we have a plan for work. We know which table we need to compact, and we even have an estimate for the amount of effort that would require, because we know the estimate for the upper bound on the number of values which are going to get written to the output table. And our task for next couple of episodes is to somehow spread this compaction work over over half bar, which I was hoping that this bar setup budget would actually explain us how to do, but well, it seems that it's just just assign things. But well, we'll definitely figure this out later. So see you next week at 5 p.m. UTC, live on Twitch and on YouTube. And again, sorry that this like thick of compaction is like very hard to grok in isolation. But luckily all the recordings are on the YouTube, so if you want to learn just about the compaction, you might want to start from 2 episodes before that, because that's where we start digging into compactions. Okay, thanks for watching, and see you next week, where we are going to compact some more.